Well, hello once again, ladies and gentlemen. Mr. Dorfler here with your very first installment of Daily Dose of Dorfler for the new semester. We're doing things a little different this year, as you realize. In the first semester, we actually did the physics. In the second semester, we're doing chemistry. Okay? So, we are going to be starting off with some information that wasn't originally intended to be kind of a fresh start type of advice to where you get the old brain gears moving, get the rust off of them. So you may be seeing early on in this very first chapter that we of the semester that we are going to kind of be just going back over some things that may seem basic, but we haven't yet talked about those. And so it's important that we go back and talk about these basic concepts before proceeding. So we are going back to chapter 1, which again doesn't really mean anything in terms of numbers. It just means that your book was designed to go through chemistry first and then to physics. So we're just kind of swapping directions here, okay? This first set of notes is actually fairly brief, okay? I know it's been a while since we've had some quick notes, but we're going to start off getting our wheels going, all right? So we are going to be discussing chemistry and the basics of chemistry to start us off this semester. Chemistry simply is the study of matter and the changes that it undergoes. It can be applied to all branches of science, biology, physics, geology, ecology, etc., etc., etc. Okay? Chemistry is involved. It's got its hands in every branch of science. Without chemistry, we wouldn't be here today. There's currently chemistry going on in your bodies, in the computers or other devices you're watching this discussion on. So, again, it's everywhere. You can't escape it. It's all with us, all right? It plays a central role to discoveries made in science and technology, and oftentimes they feed each other. Once we have new discoveries in technology, that tends to lead to new discoveries in chemistry, and then those new discoveries lead us into better technology. See how it kind of goes into a big, giant circle. So, when we are discussing chemistry, we are two things that we need to remember, and that is matter and mass, okay? There is a significant difference between what matter is and what mass is. Matter is anything that has mass and takes up space, okay? Textbooks, air, food, those are all examples of matter. What does not matter? Thoughts or ideas that are inside your head. Heat, light, radio waves, magnetic fields, feelings, emotions, microwaves, sounds, okay? Those examples that are not considered matter don't have any mass. They even don't take up space, even though you might be thinking like, oh, these thoughts and ideas are filling up my head. Well, that's just the same, okay? They don't actually have any mass. They don't actually take up space, okay? Now, mass itself is defined as a measurement that reflects the amount of matter. So, matter has to have mass and take up space. So basically physical objects. Mass is how we measure how much matter is, okay? That is what we typically will see when we say mass. That's what we measure on a digital scale when we're measuring out amounts of powders, or if we're looking at liquids, how many milliliters there are. Okay, it's our actual measurement. Okay, that's what mass is. And matter is more of a kind of a physical entity, okay? Weight. Now, again, people often use weight and mass interchangeably. Well, in some stretch, that would be acceptable. But there is, again, a difference between mass and weight. Weight is the measure of the amount of matter and the effect of Earth's gravitational pull on the matter, okay? And your weight won't necessarily be the same at certain locations on Earth, because at certain locations on Earth, there are some slight variations in gravitational pull, okay? And also, your weight's going to fluctuate on different planetary bodies. If you go to the moon, okay, where the moon only has about a third of the gravitational pull that Earth does. So your weight is going to be about a third of what it would be on Earth, okay? But your matter and your mass are not changing because that is who you are. That is how much stuff makes you up, okay? All you're simply doing, excuse me, gotta get the the voice back to normal here. All you're simply doing is changing the gravitational pull, okay? As you move away from Earth's surface, that's when you're going to start to see the slight fluctuation in Earth's pull, okay? The Earth's gravitational pull is going to be less as you move away from Earth at the sea level, okay? So why do scientists use use mass instead of weight? Mass is going to allow scientists to compare the measurements in different parts of the world. And mass is a measurement of matter that is independent of gravitational force. Okay. So it's if you want to think of it as it'll be constant. Okay. Mass will be constant wherever you go. Then we're going to talk about macro and microscopic view of chemistry. Okay. Basically, macro is, the large picture, okay? Things that we can see without the use of a microscope, okay? Much of matter and its behavior are considered macroscopic, like chemical reactions. We can see those, for the most part, with our eyes without the aid of anything magnifying it. Then you have microscopic, okay? It's in the name, need a microscope in order to observe it or see it. Many microscopic objects are composed of millions of atoms. The building blocks of matter, these are what atoms are. Okay, atoms are the building blocks of matter. And atoms will be studied in greater detail later on as we proceed through this chapter and following chapters. Then we have what's called submicroscopic, okay? Objects like atoms that are so itty-bitty tiny that they cannot be seen with optical microscopes. The structure, the composition, and behavior of all matter can be explained on this submicroscopic level. All that we observe and see with our eyes about matter depends on atoms and the changes they undergo. So it goes all the way down to the itty-bittiest little speck that normal microscopes cannot see, okay? So the goal of chemistry, the goal of this semester is going to seek to explain the submicroscopic events that lead to macroscopic observations. So we get down to the atomic level and we see what is going on there that leads to what we see with our own eyes, okay? And this can be done by making models, which we often use models to make visual representations of the submicroscopic event. We also use theories because oftentimes there are things that are so very kind of difficult to explain that we have to go to a mathematical theory in order for us to make sense of it, okay? So because there are so many types of matter in our world, we have a ton of different areas that chemistry is going to be involved in, or it can be broken down into, in fact, okay? There are typically 5 branches of chemistry itself. There's organic chemistry, okay? And this has an emphasis of carbon-containing chemicals like plastics and pharmaceuticals, medicine. Then we have inorganic chemistry, which is typically what we focus our attention on, okay? Basically, you have organic, inorganic. Organic was carbon-based. Inorganic is anything really not containing carbon, okay? Here we like to look at minerals, metals and nonmetals, semiconductors. Yes, we do study carbon itself when we have, or carbon-containing compounds in inorganic chemistry. But when we say, organic, we look at kind of like a lot of living things because carbon's involved with a lot of living things, okay? And we have physical chemistry. It has behavior and changes of matter and the related energy changes, reaction rates, reaction mechanisms. Analytical chemistry, components and composition of substances, food nutrients, quality control be examples of analytical. Then we have biochemistry. So biochemistry, it's a matter of processes of living organisms, kind of goes underneath an umbrella kind of organic chemistry, but not necessarily, because organic chemistry can involve some living things, but usually it just focuses on carbon-based substances. And we have biochemistry happening in our body all the time. Metabolism, how your body breaks down food and uses it for energy. Fermentation, okay? There's so many other examples in biochemistry that it's really a very important and popular field, especially if you go into medical fields. Other areas of chemistry include theoretical chemistry, why and how chemicals react. Environmental chemistry deals with the role chemicals play in the environment, which is, if you haven't been sleeping under a rock, you know that environmental chemistry, environmental concerns are huge. We have seen such a drastic change in chemicals in the environment over the last 10, 20, 30 years. Okay, we've seen the comings and goings of different agricultural chemicals, based on what their effects were on the environment, or even, living objects such as humans or animals. And so how those chemicals eventually have changed ecosystems, really. So many things involved there. Environmental chemistry is a huge, huge, hot subject right now. And it will be for the foreseeable future. So anyway, again, that's just kind of your brief introduction into what chemistry is, what we're going to be looking at this semester. So yeah, that's about it, folks. Welcome back to a new semester. You should have picked up, if you had the opportunity, your printed slides for you to fill in along with me as I speak. If not, I will be posting a digital copy for you to print out at home. You will need these notes as we go through here. Hopefully, once we get back to a hybrid or in-class situation, you'll also be able to, get copies from me as well. Anyway, I'm going to call it a wrap on the first video of this semester. Have a good one, everybody.